Hello, this is Miraj Patel, and today we're going to be finishing up Unit 11, which is all about states of matter, and today I'm going to be talking about phase diagrams. And so, here is a picture of a phase diagram, and notice how it shows the three phases, solids, liquids, and gases here. And so here we have temperature on the x-axis and pressure on the y-axis. So this is sort of like a coordinate grid, and it shows where a specific substance is a solid, liquid, or a gas at specific temperatures, which are on the x-axis, and pressures on the y-axis. So think of them as points. So you just use the two axes to figure out where the points are. And so, phase diagrams represent phases dependent on pressure and temperature. So just like I said, if we're given a temperature, for example, like let's just say we're given what is this substance here at 10 degrees Celsius and at 300 atm. So we would go down this axis and go until if there was a 10 mark here, but there isn't. So let's just say 10 was here, and then we go up to pressure until it's 300, so maybe all the way up here, and we would see that it's a liquid. So just know how to use this. You just use it just like a normal graph. And now we're going to be talking more about this. And so here are some important terms to know. So here we have a triple point, which is A, and triple points are where temperature and pressure make it so that all three states exist in equilibrium. So here it's when solids, liquids, and gases occur equally, so they all occur at the same time, which is pretty cool. And then we're going to talk about another point, which is point B at the very top here, called the critical point. And the weird part about critical point is that above the temperature, so on the right side of this, no liquid can exist because it's too hot. So there's too much energy in these particles here to be close together. They have to be like this. And then above this, so on top of this, there's too much pressure, so the gas is too compressed, so it has to be a liquid. So that's the weird part about this point. And then if we do have something get past this point somehow, it becomes called a supercritical fluid. So if there's something past this, like let's just say there was a gas that was a gas here, it would be called a supercritical fluid. And then now we're going to be talking about these lines. So this line here, first of all, is, notice how it's between liquid and gas. So all these points along this line represent boiling points, or they represent condensation points. So it depends on if you're heating or cooling. So if you're heating, it's boiling. If you're cooling, it's condensation. And so if we keep the pressure constant, so this means that if pressure is constant, so let's just say we're fixed with the y-axis, so we have to keep it the same. Then we have to increase temperature to get into a gas. And then if we keep temperature the same, so if we had the same temperature, we would have to decrease pressure, that's what represents a down arrow, to make it from liquid to gas. And same is true vice versa. So if we want to go from gas to liquid, we have to decrease temperature here. Or if we want to go from gas to liquid and we kept the temperature constant, we would increase pressure. So if you just think about in terms of particles, if we increase temperature, we would increase the energy, and so the particles will move farther apart and form a gas. And if you think about pressure, pressure is how much force is on the particles. So if we have less force on a particle, so pretty much if you're trying to keep in a bunch of crazy like little kids that have like sugar rushes, and if you like push them in tight enough, they'll stay together. But if you loosen the pressure, so if you like release a little pressure, that means they'll go crazy. So instead of being bunched up, same thing with particles, they'll be loose and they get free and become a gas. So that's what happens. And just remember, if we have lower pressure, we have like a lower pressure, which is down here, we have a lower boiling point. So notice how low temperature is when we have lower pressure. But if we have high pressure up here, we have higher temperatures. So this is why if you ever gone to mountains like Colorado or you know, like if you had to boil a pot on Mount Everest, the boiling point would be significantly lower than on sea level because if you think about it, there's less air pressure high up in the mountains because simply there's less atmosphere above the mountains because you're so high up. And so because there's less air pressure, look on this graph, when we have low pressure, the temperature, we don't have to heat it up much because it the pressure things holding it down is loose. So just think about those crazy kids. If we have more pressure, so if we have a more tight space, they'll they'll be tightly packed. So that's high pressure. But in the mountains, we have low pressure. So we have like a big room for these kids. And so they'll be going crazy even though we have such a low pressure. So we have a low pressure, so not much force keeping them together. So it doesn't take a lot of energy to raise them up to a gas. So that is why boiling 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 water in mountains happens at a lower temperature because there's less pressure holding back the liquid. And so now we're going to talk about another line called the solid liquid equilibrium, and guess where it is? It's between the solid and liquid states. That's how they got the name. They're not really clever about these names. And so every point along this line, just like on the liquid gas equilibrium line, is a melting slash freezing point. And so notice how again, if we have a hot, if we have the pressure the same, we just increase temperature to get it from solid to liquid. If you think about it, if we heat up the solid, the particles move faster and become a liquid and become a little bit more loose. And then if we keep the temperature the same, we just decrease pressure. So just like I said with the gas, the liquid to gas, if we have less pressure or force holding something down, that means that it doesn't take a lot of energy to increase the increase it from solid to liquid. So if we don't have much pressure or force holding back the liquids, it's easy for the particles to escape. So that is why if we decrease pressure, um, the solid can easily become a liquid. And then we have the last line, which is called the solid gas equilibrium line, or this line AC here. And so every point is a sublimation slash deposition point. Sublimation is from solid to gas. Deposition is from gas to solid. And um, so same thing. If we have lower pressure, it's a lower we have a lower temperature we need to get because again there's less force keeping them together, and if we have a high pressure it's opposite, we need higher temperature to increase from solid to gas because we have to overcome that force pushing down the particles. So that is why we get this little curve just like in these other lines. They always mostly likely curve to the right. And the important part is that below the triple point, liquids can't exist because there's such low pressure that the particles in the liquid will become a gas instantly because there's not enough force holding the liquid together. So in order to have a liquid, we have to have some pressure holding it together. So that's why liquids can't happen below this line or this point. And so here we have a phase diagram for CO2. And so notice how CO2 um, at 1 atm or 1 atmosphere, so that's normal atmosphere, that it sublimes. So it goes directly from solid to gas because it's at a low enough pressure where it doesn't go through a liquid state. And then it has a low critical point because relatively low, even though 73 atm, which is 73 times normal atmosphere's high pressure, it's not that high for critical points. And then it the temperature is only 31 degrees Celsius, which is pretty low. That's like 80 or almost 100 degrees or 90, somewhere in that neighborhood. So just like a very hot day in Florida. That's how much like 31 degrees Celsius would be. And so that's pretty low, but now we compare it to water. And water is unique because first of all, it has a very high critical point. So take that 31 degrees Celsius, but this is 374 degrees Celsius. So this is way hotter than boiling point. This is like almost 2 times the boiling point of water at normal temperatures. No. Sorry, my bad. It's like four times the 4 times the heat temperature. And it has 218 atm, so 218 times the pressure at normal sea level. So that is so much more pressure and higher temperature compared to carbon dioxide. So, and also, the reason why this happens is because of the strong IMAF. So, if you ever think of chemical properties of water, just always think of strong IMAFs. IMAFs do a lot for water. That's what makes it so unique. And the IMAFs pretty much like hold the water together, and so that's why it can stand such a high temperature and then the pressure. And the solid liquid line has a negative slope. Notice how it's the opposite of normal. So normally the lines slope to the right, so they have a positive slope. But this one has a negative slope, and the reason why is, you know how liquids are, the liquid water is more dense than solid because notice how tightly packed they are compared to the solid because there's a lattice forming. And so at higher pressures, pretty much we can just squish the ice. So pretty much at very high pressures, we can just melt the ice by squeezing it. So at very high pressures, like maybe like 200 or something, it takes less temperature to melt it because the pressure is acting as sort of like a way to melt it because the pressure is squeezing it so much that it breaks these IMAFs to form water. So that is why water has a negative slope. But you don't really have to know this. You just have to know just just how to use these phase diagrams. So you don't be too caught up in why water has a negative slope and all that. Just know how to use this thing. And so here's a quick quiz to see what you learned. So which region is the gas? And I'm sure most of you know that it is the Z region. So I'm just going to show you the answer. But let's just talk about this. And so the reason you would know that it's Z is because notice how it is on the very hot side of the phase diagram. And also gases, because at low pressure these particles will like to become free. That's why gases sort of take up the bottom half. So this one must be solid because it's at the colder side, and if this is gas, the middle one must be liquid because it's between the solid and gas, and it's at enough pressure up here to become closely packed. So just remember, solids are usually on the left, gases are on the right on the bottom, and liquids are in the middle. And now we're going to talk about the points on these graphs. So again, solid, liquid, gas. Then we have these points. So just remember these lines based off of the two neighboring phases. So if they're solid and liquid, this must be solid liquid line. Such a smart name for this line. And then we have liquid and gas. And guess what it is? You guessed it, the liquid gas equilibrium line. And then we have solid to gas. So what does this? What is this? It must be solid gas equilibrium line. So just remember, whatever it's next to, you just hyphenate the two phases and write equilibrium line. So, which point is the boiling point? So we go to where boiling happens. So boiling is the sort of like the border between liquids here and gases. So boiling is definitely between here. And notice how there's 2 points here, but 5 here is supposed to represent the top. So let's just say this was shaded and we put a box here. So 5 represents the critical point because it's at the very top. So if it's not 5, it must be 2 by default. So the correct answer is B. And so remember, when you're doing these, pick the most like clear one. So 2 is definitely only boiling. 5 could sort of be boiling, but this is more correct to say it's a critical point. And 4 could sort of be boiling because it's between liquid and gas, but this has another name for it. So always remember, when you're picking something, pick the most clear example. So 2 is definitely a boiling point, no questions about it, but 5 and 4 could sort of be argued, but they have other more important names. And so now we're asking, what is point 4? So point 4 is all the way down here, and I almost gave the answer, but I didn't. So this is why, because I'm asking you a question. So point 4 is the freezing, melting, triple, or critical point. So by the way, I just talked about critical points, so you know that's false. So critical point is actually number 5 up here, and that's when there's too much pressure for gases to stay a gas, and there's too much energy for liquids here to stay a liquid at this high temperature. So that's what a critical point is. So freezing points, let's just say which one's the freezing point. So remember, it has to be between solids and liquids, because freezing is the phase change. So solids are here, liquids are here. So 1 must be a freezing point. And melting points are also on the same line because between solids and liquid. So 1 is both the freezing and melting point. So C is the triple point. Point 4 is definitely here, and it's a triple point because it's where all 3 phases occur together. So think of triple as 3. So think of where they all occur. And then, so we sort of went over these phase diagrams. So just remember, uh, temperatures on the bottom, so on the x-axis, pressures on the y-axis. And so just remember how to use this. So you just use it like a normal grid. So if we say the temperature is 200 and the pressure is 10 atm, we'd go all the way up here and we could figure out that it's a solid. So just to know how to use this grid. And then also know the 3 regions, so solid, liquid, gas. Know these 3 lines. So this is solid gas equilibrium line, solid liquid equilibrium line right here, liquid gas equilibrium line here, and know what kind of points these are. So between solid and liquid, it's melting and freezing. Between liquid and gas, it's boiling and condensation. Solid and gas is sublimation, deposition. So know these 3 lines and their states that they're next to and what phase changes they represent. Know the critical points are up here, and know what it is, and then know the triple points where all 3 occur together. And so that is it for Unit 11, which is all about phase changes and phase changes and temperatures, exothermic, endothermic, IMAFs, and all that stuff. And so the next unit is going to be all about solutions. And we're going to be talking about equilibrium of solutions. So that's going to be fun. And so I'll see you later, and I hope you have a good day.